and these are two UK organizations that look after our bioenergy transition. So I wanted to start with a very brief introduction. I'm a bit of a strange person. I have 8 jobs officially, which is with 8 different organizations, which is very exciting. Unfortunately, only 3 of them pay me, but such is life. So I'm an academic at Imperial College in London, and as I mentioned, I'm co-director of the United Kingdom's national organization that looks after research in bioenergy, Supergen. And I'm also a serial entrepreneur, and I've founded 7 different spin-out companies and startups over the past 7 or 8 years, most of which work in the bioeconomy. The most prominent one, which is Lixia, which is listed at the top, is actually a European company that we founded in 2017 that builds biorefineries. And Lixia is going to announce in about 2 weeks that they are building their next plant, which is a 25,000-ton demonstration plant in Eastern Europe. I'm not allowed to say exactly where. I wanted to give a very brief background on the organization I am representing today, which is the Supergen Bioenergy Hub. It's, as I mentioned, the research program that coordinates the UK activity in bioenergy, and it spans the entire United Kingdom. And actually, we have a lot of partner companies also from Europe. And our aim is to increase the use of biomass within the UK economy. And we look at everything from district heating through to hydrogen and chemical production. And it's a combined sort of academic-industrial collaboration. We have activities in policy intervention within the UK government, but also a lot of member companies that work with us on accelerating the industrial transition of some of these research activities. I don't know as much about BBNet because I'm not a member of it, but it's a mostly industrial community within the UK that works on, as a network, to coordinate also activities where people can share knowledge about the bioeconomy. Okay, so I'm going to talk very briefly about the chemical transition as we see it in the UK, and start with the business as usual part, which is always a little bit depressing, about petrochemicals. As everybody knows, especially at this conference, petrochemicals are everywhere. And we often think, of course, about fuels, and so petrol and gasoline as a primary product, but of course, practically everything that we make and use in everyday life involves petrochemicals. Very famously, of course, more than 99% of plastics are petrochemicals, but also nearly 100% of detergents are petrochemicals. 100% of dyes are petrochemicals. And so practically everything that we use is a petrochemical project right now. While we have a lot of activity and a lot of commercial success in trying to transition into renewable energy, there hasn't been nearly as much in the renewable chemicals space. Materials, in fact, have started to outstrip chemicals in terms of their ability to transition. And there are a lot of reasons for this. Most of it, I find, comes down to a more political concept around decarbonization. And of course, anything that's an organic chemical or organic material is quite literally impossible to decarbonize in the absolute sense. There has to be carbon contained within the material. And so we have to talk about the transition in terms of defossilization, which is a little bit more difficult to communicate, especially within the policy sphere. The second challenge that we face is that the emissions are a little bit more diffuse along the supply chain. So there are, of course, emissions that are involved with feedstock sourcing, and there are emissions that evolve during the processing itself, so the processing of the raw material feedstocks into the products, and then, of course, the carbon that's released during the processing itself and at the end of life. And the 3 arrows on the right are in common between bio-based products and petrochemical products. The energy involved in doing a biological process is normally higher than in a petrochemical process. The emissions, the CO2 that's released during processing, something like fermentation, is much higher than it is during petrochemical processing, and the end of life is virtually identical between the two. Biodegradable products, of course, they release that that carbon a little bit faster, but it's generally speaking the same amount. And so the big place where the emissions reductions are going to come in is, of course, on the feedstock sourcing. And so figuring out how to get enough carbon negativity into the feedstock production in order to counterbalance everything that's going to be released during the process. And with fossil reserves, of course, we have no ability to do that. And so this, of course, has led to the concept of the circular bioeconomy, which takes in different, well, I guess you could say renewable, or rather than low carbon, feedstock materials, and makes these products that we want to use in everyday life. I'm focused, and this report is focused entirely on biomass as a feedstock source, but I'm not personally discounting anything to do with recycling or CO2 conversion. It's just not the focus here today. And I think, for me personally especially, I'm a researcher that works on a lot of sustainability concepts outside of biorefining even, so a lot of circular economy and recycling projects. There are a lot of impacts of using petrochemicals that have very little to do with greenhouse gas emissions. At the moment, virtually everybody in the world is very focused on climate change, which is a good thing. But it is important to remember that there are pollution aspects to doing chemical processing, and we don't want to end up in a trade-off scenario where we develop a bio-based product that might have a lower carbon impact than the chemical it's attempting to replace, but increases pollution potential down the supply chain. And you see this a lot with different, especially fine chemical products, where we don't know what the end of life is going to be of especially things like surfactants and dyes, which have a moderately high impact in the environment to begin with. Thank you. So, the next few minutes I'm going to go over a very brief overview about making chemicals from biomass and how we see this transition being incorporated. There are sort of two options for how you might institute bio-based products into the economy. One is to run dedicated biorefineries. This is my personal specialty, but it's not the only option. And here we would be attempting to replace the function of chemicals and materials within the economy. So trying to develop bio-based analogs or bio-based replacements that either have similar or hopefully superior properties to the existing petrochemicals. And we heard just a few minutes ago a couple of examples of where that can take place. And here you want to leverage the opportunities that are within the product performance sphere. The other option, of course, is to go through the same intermediates that the chemical industry uses right now. And so find a way to get, or find the best way to get to syngas or ethylene, and then we can run existing petroleum refineries with bio-based feedstocks. This is the extreme example of the mass balancing approach that BASF and other companies have been championing, where we can utilize existing assets within the economy. This leads to a much lower cost product base than you will get with practically any biorefinery concept, but probably a much lower emissions reduction than you will get from going to a solely bio-based route. But in the end use products are, of course, what the consumer has to accept and what the economy has to accept. And so we have to be making products that people will use. And so this leads to a lot of challenges in terms of translating bio-based materials into the economy. And there are, of course, a lot of bio-based chemicals on the market. 100 years ago, there were nothing but bio-based chemicals on the market. We slowly but surely drifted away from this. When talking to students, I often talk about the different products. Linoleum was the first plastic that we made. It was entirely bio-based. Now we practically don't make any. Vanillin is one of my favorites because it was 100% bio-based, and then it was 100% petroleum-based, and now it's sort of transitioning back, but we kind of do this back and forth. Ethanol was 100% bio-based, and then it was nearly 100% petrochemical, and now it's gone back to being, last I saw, about 70% bio-based. And so you can see these things swing back and forth over time. But on the whole, the market is still, at present, completely dominated by petrochemicals. And this leads to a lot of challenges in establishing bio-based chemicals and materials in the market. Competition is, of course, the big one, because this leads to these questions of cost. Why do bio-based products always cost more than petrochemical products? And the answer is effectively that established capital, that infrastructure I mentioned a moment ago. Scale up, we just had a huge session here this morning on scale up. Scale up is of course a massive challenge because it takes a lot of time, it takes a lot of energy, and it takes a lot of investment in order to bring these bio-based chemicals and materials up to the level of production where they can compete in the marketplace. And you can achieve something resembling cost parity with a lot of bio-based chemicals, but it's very difficult to do at small scale. And so this is something that will take time. Depending on where you are, the UK is not a particularly biomass-rich country, but depending on where you are, you may or may not have difficulties with feedstock availability. This ought to be an advantage for bioprocessing because it can utilize a wide variety of feedstocks. Also, I always have to send out a reminder when people talk about feedstock availability, it's not as if our petroleum reserves are widely distributed around the globe at the moment either. And so how we manage that transportation and infrastructure challenge is a bigger deal than just sort of throwing out there that feedstock availability is a problem. It's not always. And then, of course, there are questions around policy and the big one around sustainability. And every time a bio-based product makes it to the market, there's usually an immediate backlash about whatever aspect about it isn't particularly sustainable. And that transition is also going to take time. We can't expect these products to be 100% sustainable immediately. I always marvel, especially with bioplastics, how we give a complete, this is a side note, but we're okay with all of the deficiencies of petrochemicals. We've somehow accepted them. Whenever a bioplastic or a biomaterial comes in with some deficiencies, it's immediately thrown up as a massive red flag, even if the chemical it's attempting to replace is much worse. That doesn't seem to matter very much. But anyway, just a rant. I think that sustainability question is very, very important, though. And since there is some element of responsibility or producer responsibility that goes into this transition, we have to understand very well the dynamics of how these sustainability questions are going to be answered over time. And I mentioned earlier that the bio-based version of a petroleum refinery does still have emissions, and we do have to accept that. If you have a literal bioprocess, probably half of your carbon is going to be exiting your fermenter as CO2. If it's a chemical-based, so a bio-based process where you're not doing bioprocessing, but you're doing a chemical process on biomass, that can be greatly reduced. But there is still going to be some carbon losses along the supply chain, and that isn't a unique factor either. And these have to be offset by the carbon sequestration that happens from growing the biomass in the first place. And this is a lot of why we talk often about the carbon cycle as being a little bit more fluid with bioproducts. How long the product lasts is very important compared to how quickly the crop will grow. And in Supergen, we've done a lot of examination of existing literature data as to how sustainable the bio-based chemicals are compared to the fossil-based analogs. And I had to stare at this graph for a long time before it started to make sense to me. But effectively, it is a carbon intensity graph. So we have a lot of products and how carbon intensive they are based on a life cycle assessment of how the literature proposal of that process would work. And that is, yes, that is somewhat of a translational concept to how the industrial process might look. But unfortunately, that was the best we could do. And there isn't an easy take-home from this. I mean, there aren't a lot of carbon negative products and processes that are out there, but there are some. And on balance, I would say greenhouse gas reductions switching from a petrochemical or a fossil-based process to a bio-based process, carbon reduction is possible, but it's not guaranteed. When it does happen, it's usually quite significant. But there are a lot of examples where it isn't a more carbon efficient route to use a bio-based process. So if all you care about is carbon reduction, if climate change, CO2 emissions are the only thing on your political agenda, bio-based products aren't always the answer. It should be fairly obvious, but it isn't always. The way to handle this is to prioritize the case studies where the bio-based product does have a significant GHG savings, and perhaps deprioritize cases where it doesn't. So this is a fairly straightforward answer to the question of feedstock availability. is to set your priorities according to the performance indicator that you want. So if you're after greenhouse gas emission reductions, target the products where you get the most greenhouse gas emission reductions. I also, of course, always put in the caveat that we use life cycle analysis as a tool to examine this, but it is not an absolute answer in and of itself, and it is greatly dependent on the information at its disposal. And often we are taking a projection of what a biological process might look like compared to the reality of what the chemical process that's been refined and optimized over 100 years actually is. And so there is a little bit of room for interpretation in terms of what can evolve in this sphere as these technologies reach a higher level of maturity. It is a little bit more controversial to talk about negative emissions, but this is an area where I guess bioenergy or biomass processing has a massive advantage over all other renewable technologies. So it is virtually impossible to electrify something and get negative emissions out of it unless your electricity is carbon negative. And the only way to have carbon negative electricity that anyone has yet proposed is to use bioenergy. And so how we balance those negative emissions across the economy is actually quite important. When you put bio-based carbon or biomass-based carbon into long-life products, of course, you get sequestration on the back end also. And so you can have carbon sequestration in your feedstock and carbon sequestration in your product. And so again, if this is the greatest source of greenhouse gas emissions, this could be an area to prioritize. But I do think that there are opportunities, of course, to look at integrated carbon capture. This happens a lot in biorefineries, where the CO2 from the fermenter, which is classified as biogenic carbon, is captured and utilized elsewhere. And so those sorts of opportunities also can contribute. And the sort of last thing, oh, we're good on time, so almost perfect. The last thing that I wanted to mention was about other areas of sustainability. And as I mentioned, this is very important to me personally, because I sometimes feel, especially in the academic space, we get a little bit too obsessed with carbon intensity, as if climate change is the only problem the Earth has ever had. And you see a lot of, especially small companies, pivoting to bio-based products where the pollution aspects are actually much, much greater than they were with the petrochemical analog. So perhaps a lower carbon intensity, but a higher pollution potential. And I personally don't think that that's a great trade-off. I think that we ought to be looking at a more holistic version of what we should be doing. What is the most sustainable option? And this often comes up in the sphere, unfortunately, of plastics. And a lot of bio-based plastics actually have bigger processing problems than the petrochemical analogs. But besides climate change, of course, we have to think about water quality, reductions in biodiversity, so handling our biomass feedstocks in a responsible manner. I mentioned pollution. But also, how does this contribute to jobs in the economy? So how is economic growth going to be impacted by this transition? And so there are a lot more aspects of sustainability than just greenhouse gas emissions. This gives you a lot of potential benefits from a bioeconomy, but there are some risks because, of course, we will be ripping up the economy as we know it and replacing it with a new ethos. So we don't have perfect recommendations at the moment, but I do think that if we want to maximize the contribution to climate mitigation, as I mentioned earlier, the applications where you see the greatest decrease in greenhouse gas emissions from bio-based products come when you prioritize certain applications, where you look at sectors that can't be decarbonized in other ways, so products that have carbon embedded in the product itself, and applications that provide opportunities for negative emissions. I mentioned bioprocessing or bioenergy production where carbon capture is built in. And that does lead to the conclusion that we might want to prioritize certain chemicals. The reason chemicals come up a lot is because they are made out of carbon. And so the decarbonization does require still a carbon-based source to make the chemical in the first place. The UK, of course, it does still have a chemical industry. It's sort of pivoted from the historic heavy-duty petrochemical base to a much more distributed manufacturing scheme. And moving forward, of course, we're trying to coordinate the industry and academic and policy aspects through this research and innovation space to transition that economy. It's actually quite difficult in the UK because a lot of our feedstocks are imported already, whether it's biomass or whether it's oil and gas. The UK's feedstock base isn't as rich as other countries are. This does present a lot of challenges. So, our biggest recommendation at the moment is to try and really do things like this. Talk about the opportunities that exist and try and secure consensus on what the best path forward is. We're working at the moment to develop a roadmap for this. So how actually do we navigate this transition? And how do we improve sustainability governance within the economy so that the bioeconomy doesn't start having these sort of negative stories associated with transitions that we're attempting to do good in the world, and then ultimately to implement policy to accelerate this transition. That should be the end of my presentation. If you want to download the entire report that I just summarized, there's a QR code there. And from here, I'm happy to take questions, and then we'll have the panel. Thank you.
Thank you for the nice presentation. I'm interested to learn what would happen with your greenhouse gas curve if you would deduct the biogenic. Because we're talking about long lifetime products.
Yeah.
Corn or others, they grow every year and take up CO2, but still we are not allowed to use that as a negative due to regulations. So it would be nice to see what happens with your curve.
It is a fantastic point. I have to say, I don't know the answer to your question, or I don't know what would happen to the curve, I guess, offhand. I would say that is probably the biggest regulatory hurdle that we see in this space is, I don't know what to call it, a skewed accounting of how to look at greenhouse gas emissions, because as you rightly point out, crops take CO2 out of the atmosphere on a very short lifetime. So, especially in bioenergy, where you grow crops and then incinerate the crops, and this is counted as a CO2 emission, but you don't get credit entirely for the deduction for the growth in the first place. Or when you look at corn ethanol or wheat ethanol, where we look at the emissions that come from the fertilizer, from the growing of the crops, and from the transport of the crops. But we don't look at the negative emissions associated with the production in the first place. I think the issue is that it is quite variable, because a lot of it depends on how much of that resource is captured, and so how much is left in the field versus how much is taken in. But yes, I do think challenge number one is to do a more accurate accounting of how this works. Quite famously, there's 100 billion tons of cellulose produced on Earth every year by plants without our intervention. So this happens whether we want it to or not. And so that's sort of a carbon budget you could think of that we have to work with. That's the scale that we're competing against. The chemical industry only processes about 350 million tons of carbon. And so it's actually 3.5 orders of magnitude below what nature has in its cycle. So we have to think about how to work within that. But it's a great point.
Yeah, thank you for the presentation. I have two questions. The first is long lifetime products. From an LCA perspective, it's no difference in impact if you have one long lifetime product or you replace in packaging 20 times short lifetime products. So it's generally better to have long lifetime for fossil and bio, but if you replace, the replacement has the same impact for long life and short time, so we should perhaps not only focus on long lifetime products. That's my first question. And the second is, you have avoided to use the word defossilization. Also, that would fit perfect to your argumentation. Is there any reason for that? Because you say we have embedded carbon in chemicals and plastics, and the way is to defossilize it, not to decarbonize it, because it is not possible.
Yeah. Well, we'll start with the second question first, because it's a little bit easier. Yes, exactly. It's a semantic point. So it is about the language that we use, but I do think that it is important to get that right, because it isn't that the carbon is evil in carbon-based products. So it's the emissions that are the issue, not the carbon itself. And so we have to think about energy usage. This is a universal challenge. No matter how we do our production, we have to think about energy usage. But the embedded carbon is something that we have to deal with. And I guess part of the question is how best to deal with it. So to your first question about long lifetime products, our recommendation is more that that's a priority, a prioritization question rather than an absolute answer. So I do think we should look at both. I personally work more on short lifetime products than long lifetime products. So I'm sort of on the other side of this. It's just that on the long lifetime products, there's a lot more political acceptance. There's a lot more drivers for those to transition to bio-based. I do think it's a fun, I do a lot of outreach, as a lot of people do, talking to the public. And this is where we do a very bad job of communication, because the public wants everything to be biodegradable. And you have to step back and say, well, look, there are some things, packaging is where that sort of crosses over, right? There are some things where you do want it to be biodegradable, and there are some things where you absolutely do not want it to be biodegradable. And then there are elements, packaging is a great one, where either you want it to be biodegradable, you want it to not be biodegradable so it will function, and then we have to collect it very carefully and we have to dispose of it in a responsible manner, or you have to accept that the human race is incapable of dealing with packaging in a responsible manner, and so we're going to make it all biodegradable so that we can continue throwing it into rivers and oceans at our whim. So I guess it depends on how cynical you are about changing people's behavior.
When I talk about short life, I was not thinking about biodegradation. In biodegradation, the European Commission has a clear standpoint and we share it. It's only for risk minimization. That means if some products have a high risk to enter in the environment, then they should be biodegradable, like fruit stickers, for example, but it's not a general solution at all. But when you say there is a better policy framework for long life products, I think we as a scientists have a responsibility to inform the policymaker in the right way.
Yes.
And we have this discussion with the environment almost every day, that they're not making the wrong proposals. And so it's important to say them from the LCA perspective to replace short-time packaging by bio is also a great thing, and not only long lifetime products.
No, I agree. I do agree with that. I guess it's more of a question of what order we do things in, and it's a little bit easier to work within the framework right now and change it on a little bit of a longer time scale. But I do agree with you. We may have gotten that one backwards.
Thank you very much.
It's more your point of view. Biofuels like biodiesel get subsidized, but several of products used today to produce this biodiesel are very good products to be used for other type of applications, consumer goods. Tall oil fatty acid, for instance, is a very good example of that. Yes. Gets subsidized for biodiesel, and therefore it's not available anymore for consumer goods or for coatings, etc. What's your point of view towards politicians?
So first of all, I personally like biosubsidies, but at least half of the politicians do not. So that is a very controversial space. I think the problem with subsidies in general is that they are subject to change and political whims, in fact. And so there isn't, in a lot of countries, there isn't enough confidence in the long-term application of those subsidies to spend €500 million building a refinery when the economics of it may change in a 5-year time span rather than a 20-year time span. That aside, I actually think that we've gotten the subsidies on the fuels versus chemicals completely backwards. I would much rather see those subsidies applied to making products than to making fuels. It's actually much easier to decarbonize transports or defossilize transport in multiple ways. So we have a lot of options there. It's very difficult to electrify materials. You can electrify their production, but it's very difficult to make plastics out of electricity. You need some feedstock. And so the transition there in encouraging more electric vehicles or whatever is a little bit easier to digest than trying to do the same thing in the chemical sector. So I would much rather see those subsidies reversed. But that's, again, politically very challenging. It's very easy to do transport, and it's very difficult to do manufacturing.
All right. Thank you very much. I think that's a great